Thank you very much. I guess the very first thing I should say is that I know very little about p-Adic Langlands, so I'm a little bit uncomfortable talking about it. So my vague understanding of this is the following. So what's p-Adic Langlands? Sort of based on the GL2 case, I guess you would take a finite extension of QP, and some continuous representation of the Galois group. by gamma k on some p-Adic field. So this is some finite extension of QP. Which is sufficiently large to contain the Galois closure of K, for instance. And I guess what you're trying to do is you want to attach some Banach space, some B of rho. So this would be a Banach space over the coefficient field. Which has an action of GL and K. Okay? So somehow endowed with some unitary admissible, in some sense, action of GL and K. Which should satisfy various compatibilities, and you should somehow be able to recover rho from that Banach space. So from which one can recover the representation rho, right? And satisfying all these compatibilities. So as far as I know,
you mean isometric, not unitary.
Yeah, I mean it preserves. Huh?
You mean isometric and not unitary.
Yeah, it preserves that norm, right? Yeah. So as far as I know, the only case that's really understood is GL2 over QP, which I don't really know that all that well. But what I do know is the following. So if you just look at GL2 QP, so this whole enterprise of Orsay, Breuil, notably Colmes, and Emerton, Descunas, and so on, where you can actually define this P of rho by looking at the phi gamma module and then composing with this Montreal factor, which really has no generalization to GLN. So the properties that I want to point out are the following. So this really associates a Banach space to any continuous representation. And you can detect when that's potentially semi-stable by looking at the algebraic vectors. But the first thing is that if you look at B of rho and look at the locally algebraic vectors, then this is non-zero. precisely when rho is potentially semi-stable. And it has distinct Hodge state weights. Typical mess. And if you put yourself in that situation and take something that is potentially semi-stable with distinct Hodge state weights, then you can actually describe these algebraic vectors in terms of the local Langlands correspondence. So if rho is potentially semi-stable with with Hodge state weights, be careful about the normalization. So 0 and 1 minus k, with k at least 2. So I guess the Hodge state weight of the cyclotomic character is minus 1. Then you can describe that subspace as just being some symmetric power. So some algebraic representation, tensor some smooth representation. Pi of rho. So this pi of rho is essentially just given by the local Langlands correspondence. So there's this recipe of Fontaine. Which associates a very Ling representation. And you Frobenius semi-simplify. And then by local Langlands, you get this pi of rho. Essentially. Except when pi of rho is non-generic, you have to replace it by some parabolic induction. So this is really what's called generic local Langlands. So as I said, if it's non-generic, you have to write it as a quotient of some parabolic induction and then replace it with that parabolic induction. Generic local Langlands correspondence. So one thing it implies is that you can think of B of rho as being some suitable completion of this locally algebraic representation. So this is the symmetric power. Will do. And then this pi of rho. Where you take the completion relative to some invariant norm. This completion relative to some suitable invariant norm. Right, on that space. At least if rho is irreducible. Okay. In which case this is known to be topologically reducible. So there's this conjecture of Breuil and Schneider, which tries to mimic this for GLN. So let me try to state that. So now you start with an n-dimensional potentially semi-stable representation. Let's set up some notation. So now you consider some rho, which is a representation of gamma k. L is large enough, and this is potentially semi-stable, and let's say it becomes semi-stable when we restrict it to to some finite Galois extension. So let's say rho restricted to gamma k prime is semi-stable. Right? We take k prime over k in some finite Galois extension. We're going to fix throughout. And then you're trying to play the same game. So you still have that recipe of Fontaine. So corresponding to rho, you have this filtered phi module. So by Colmes and Fontaine. You know that there's a way to associate some filtered module. It's called D. So this D PST of rho. So this is some free module, rank n, this tensor product. And it has this Frobenius, and it has a monodromy, and then it has an action of that Galois group. So it's a module. And it has this admissible filtration. Some filtration, not on D, but you sort of have to extend scalars to K prime. Right? And conversely. And if you forget about that filtration, you just get a phi n Galois module, which corresponds to a Wedelin representation. So first of all, you get WD of rho. So this is a Wedelin representation. N-dimensional over L, which becomes unramified when we restrict it to K prime. So this is this guy. And if you just record the jumps of that filtration, you have the Hodge-Tate weights. Let me label those. So you get HT tau of rho for each embedding of K into L. It's just these integers. I'm going to call W1 tau less than or equal to W2 tau. Wn tau. So they're just the jumps of the filtration. That factor. And we're always going to assume that these Hodge-Tate weights are distinct. Strict inequalities. And out of these data, you can construct a locally algebraic representation. And what's the Breuil-Schneider conjecture? So they conjecture that that locally algebraic representation, which I'm about to define, the psi of rho, tensor pi of rho, at least admits an invariant norm. Admits a GLNK invariant norm. Okay. So for the rest of the talk, I'm going to call this BS of rho. So how do you define this? So what's the recipe? So the algebraic part is just by mimicking how you go from Hodge-Tate weights to the highest weight. So how do you define psi of rho? So the normalization is a little bit off, so let me be careful. So you introduce the following. So introduce numbers b, j, tau. So this is defined to be minus wn plus 1 minus j tau, and then minus j minus 1. Right? So since you assume that the Hodge-Tate weights are distinct, this really defines some dominant weight. And you take the corresponding irreducible algebraic representation. So you define psi tau to be the irreducible algebraic representation of GLN U over L of that highest weight. Right, so it's B1 tau less than or equal to Bn tau. Right? Relative to the lower triangular graph. And you define this to be the tensor product. Or all these embeddings. Right? And view this as a representation of, I guess, GLN K tensor L. And again, pi of rho is essentially just the local Langlands correspondence. So what's the smooth part? So you look at that Wedelin representation. Frobenius semi-simplifying. And then pi of rho is this guy. And with that normalization, you have to take the power n minus 1 over 2. Right? And again, if it's non-generic, this is not really true. You have to replace it by some parabolic induction. Which maps onto that pi. Right? So I guess what you hope is that this norm should somehow correspond to this filtration. But I don't know. if anybody knows exactly how that goes. So let me just mention that there's a converse, which has been completely proved. So let's use this as a remark. So the converse was proved by a student of Breuil. His thesis. So what do you mean by the converse? So you can really start from just abstract data. So you're given some Weidelin representation and some set of integers. And you could use the same recipe and produce this locally algebraic representation. So from abstract data, some Weidelin representation and some tuples of integers. The very same recipe gives you some locally algebraic representation. And you can ask, when does this data come from something that's potentially semi-stable? And well, the conjecture is that that happens precisely when this guy has an invariant null. And in that sense, who proved the converse? In fact, he proved a lot more. So what he proved was the following, that this data arises from something potentially semi-stable. In other words, you can find a filtration which is compatible with the data. There's no filtration. If and only if some technical condition is satisfied, which is called the Emerton condition. So this guy satisfies the Emerton condition. So I'm going to refer to as EC. So it's really some sort of p-Adic analog of this Kesselman criterion for square integrability. So what it says is the following. We won't really need it, but you can look at the Geraghty module of this guy. Defined in the locally algebraic context by Emerton. And you can look at the central characters. So you have this contracting monoid. And you take a character occurring in that Geraghty module, then this should be integral. In the sense that delta p inverse chi of c is p-adically less than or equal to 1 for all c in that monoid. Right. So it sort of looks like Kesselman's criterion. So in other words, the existence of that filtration is translated into this purely group theoretical condition, which makes sense for any group. Right? So this is really purely group theoretical. And yeah. So you take the Geraghty module of this guy, and you look at a chi that occurs in there, and that should be p-adically integral. If it's non-zero, yeah, sorry. Right. So this is whose thesis? And then in comparison, it's relatively easy to show that if it has an invariant norm, then it satisfies the Emerton condition. Right, so this was first by Emerton. It's really not that hard. Right? So if there's a norm, there's a filtration. Right? So the conjecture is the exact opposite, that if there's a filtration, you want to somehow produce a norm. And this was really only known in very few cases. So if the Wedelin representation is irreducible, in other words, when pi of rho is supercuspidal, I mean, you can construct this norm by compact induction or taking the sup norm of matrix coefficient and so on. It's not that hard. But if you try to push that a little bit and look at the indecomposable case, you need another argument. So I found this short proof a couple of years ago, which proves a special case. In fact, which is mentioned explicitly in their paper, that this holds if the Wedelin representation is indecomposable. Okay. So in that case, this condition is really simple. So what this means is that pi of rho is what's called generalized Steinberg. And you can compute the Jacquet modulus of those guys. So if it's non-zero, it's simple. So this really simplifies tremendously. So you only need to check that Emerton condition when p equals g. Okay. Right. Which is really just saying that the central character is integral. So to prove the theorem, you prove something stronger. So it suffices to show the following. This is really just group theoretical. So it suffices to show that if you take any connected reductive group over QP, and you take any algebraic representation, so take psi to be any irreducible algebraic representation of G, let's say, over QP bar. And you take pi to be some discrete series representation, or more precisely, some essentially discrete series of that p-Adic group, with coefficients in Q bar, which is sort of identified with the complex numbers. and take the tensor product, then that has an invariant norm if and only if the central character is integral. Invariant under G of QP, if and only if the central character is unitary. Right? Obviously necessary, right? So this is really just the Emerson condition in that case. And you infer that there is a norm. So if you take G to be, just jurisdictional scalars, GLN, you get that there. So I'm just going to try to sketch the proof. It's really a simple idea. So what's the proof? Sketch. So this is for any connected reductive group. And the first thing you do is you reduce to the simple case, right? So you may assume G is simple. It's a little bit of bookkeeping, but you just pass to the derived group, and you pass to the simply connected cover, and write it as a product of simple groups, and you produce a norm. And in doing that reduction, you need that condition on the central character. Right, when you pass from G to the derived group. But once you assume it's simple, this, of course, is completely vacuous. Right? There's no condition. So in the simple case, you should always be able to produce a norm on that locally algebraic representation. And the way you produce a norm is by passing to a global setup. So you pick some model, some global model of your group, which is defined over Q, and which is compact at infinity. So this is really making use of a computation of Breuil and Harder, that you can prescribe these forms locally, because they're not inner forms, they're just forms. So you pick a group, and then there's an old argument of Clausel that you can sort of embed this in an automorphic form. So since pi is a discrete series, it has a pseudo-coefficient. It's really just a function on that p-Adic group that behaves like a matrix coefficient. And if you plug that into the trace formula, which is really simple in this case, there's this argument of Clausel that allows you to produce an automorphic representation pi of GA such that at infinity it's your given psi, and at p it's that given pi. Right? And Then you use algebraic modular forms to produce that norm. So what I claim is the following. That if you look at psi times the finite part, that has a natural norm. This has a GAF invariant norm, which is more or less canonical. And then if you restrict it to the piece component, of course you deduce that psi times of pi has a GQP invariant norm. And to produce that norm, you use algebraic modular forms. So you can think of pi f as sitting inside I'm going to call A G psi, which is by definition just the arms from psi into the space of smooth automotic forms. And that's a smooth representation. So this is really just a direct limit or union or compact open subgroups, and then A G psi k. This is just a base of modular forms on that group. And then using that isomorphism, which is lurking in the background, you can think of these as p-Adic modular forms. So via iota, you think of this space as just a space of p-Adic modular forms. So this is just identified with the arms from psi into the space of continuous functions on on a certain quotient. So CG is just the space of continuous functions. On this quotient, taking values in QP bar. Okay. It's just algebraic modular forms. These are the classical p-Adic modular forms. On G. And this obviously has an invariant norm, which you want to restrict to this guy. So this implies when you look at psi times of pi f, well, and this sits inside the direct limit or the union of psi tensor these arms. Okay. And by evaluation, this sits inside CG. Okay. You check that everything is compatible. And you just restrict the sup norm to that submodule. And you're done. Okay? So it really produces a bunch of norms. There's many ways to, first of all, pick G, and once you pick G, there's many ways to pick pi. So So it really produces a host of norms. And you can push this argument to make progress in a decomposable case. So let me just say a little bit about that. So what about the decomposable case? Which is way harder. So now you want to go back to the GLN case and take this G to be a unitary group. So let's put ourselves in the following setup. So you take K over F to be some CM extension. And you take U to be a unitary group. With a totally real field, which becomes some inner form over K. And this is some inner form of GLN. And you take G to be the corresponding group over Q. So the restriction of scalars of U. And you always assume that this is compact at infinity. Okay? So you assume that G of R is compact. This is compact. And at P, you want a bunch of GLNs. This is compact, and G of QP is the product of GLNs. So you take places above P of F, and you take GLN of K V tilde. Okay. So at each place V, you pick some V tilde of K above P. Okay. So it's really just corresponding to choosing a ordinary CM type. And sort of a convenient formalism in which to state the result that makes use of eigenvarieties. So let's pick some eigenvariety. So it really depends on the choice of the same level. So this is some rigid analytic space defining with some finite extension of QP. So reduced rigid analytic space, which sits over weight space, which parameterizes the locally analytic characters from T of QP into GM. Okay. So this is finite morphism. I'm going to call it chi. And it has more structure. So this really carries an eigensystem. So some homomorphism lambda from the spherical Hecke algebra into the ring of functions on X. And it has this Galois pseudo character into O of X. And there's a dense subset of classical points. Let me place. And it has this Zariski then subset. Oops. XCL. Let X of Q be bar of classical points. So what do I mean by classical points? So it means, first of all, that we look at chi x, and that should be a locally algebraic character. So it should be some algebraic character, and some smooth character of the torus. And there should be an automorphic representation of G, of weight psi x, such that when you look at the component at P, you should embed inside that principal series. And moreover, it should have vectors fixed by Kp. So they should be non-zero. And the Hegel algebra should act by lambda x. Okay. So these were constructed by Emerton and Bellaish and Chenevier. And we're not really going to use much. It's just a convenient way to state the result. So pick your favorite construction of an eigenvariety. And then once you fix the coefficient field, so some final extension of the field of definition, and you fix a point defined over that coefficient field, then first of all you can associate, well, you can specialize that Galois pseudo character. So you get a Tx, which is the trace of an actual representation, which may or may not be defined over L. So this is some n-dimensional pseudo character into L. And you can also associate a certain Banach space. So you have Tx, and you have what I'm going to call Bx. So by definition, Bx is just a space of continuous functions, as before, on that quotient. But then you only take those that are right invariant by under Kp, which maps into L. Continuous functions, and then you take the eigenspace. You take the lambda x eigenspace. Okay. So this is a Banach space, and it's a lot more than that. It's a Banach module for the completed Hegel algebra. It's going to call H Kp hat. Okay. So concretely, this is just a space of functions vanishing at infinity. And which are bi-invariant under Kp. So it's a Banach Eigen module, which also carries an action of G of Qp. So with a unitary or isometric action, a unitary DQP action. So in some sense, this is what you would call global p-Adic Langlands. So in other words, once you fix an eigenvariety, you get this one-to-one correspondence between things of this form and things of this form. Right, so a correspondence between pseudo-representations and Banach Eigen modules. Right? So some sort of global p-Adic Langlands. And what you want to do is you want to compute the algebraic vectors of this guy, which you can do. So this is essentially just local global compatibility at P. So to state the result, let me just make some simplifying hypothesis. So let me assume the following. That you pick a same level such that the ramified places are all split. You have split ramification. Okay. So local base change is defined everywhere, and that pi is uniquely determined. So what's important is that this implies that pi is unique for a classical point. If you assume that rho x is globally irreducible. Okay. And what are the algebraic vectors? This is really the key input. So you make that hypothesis, and you take a classical point for which rho x is irreducible. And for simplicity, let's assume that the multiplicity of pi x is equal to 1. Perhaps that's always true. I don't know. Let's put it in there. Then you can express that space of locally algebraic vectors as just the tensor product over all v above p. And then you take that Breuil Schneider representation of rho x restricted to gamma k v tilde. So that's your representation of d of qp. And then censor some Eigen module, which is just your pi x. So this finite dimensional space. Okay. Right. Except that there's this problem with the normalization. So it's really only up to a twist, which doesn't really do much. So maybe I shouldn't say that, but it's just this Breuil Schneider representation up to something which is unitary. So maybe I should just ignore that. So in particular, you can just take your norm on bx and restrict it to these guys. Produce a norm on these locally algebraic representations. And I should say this is essentially, so certainly the key input is this local global compatibility at P. Due to Barnet-Lamb, Toby, Geraghty, and Taylor, and Caraiani. So you can use that to produce norms and get the following. So just end with this, which applies to the decomposable case. So you keep the same hypotheses, split ramification, and classical point, which is irreducible, multiplicity 1, so on. And then I claim you can construct the candidate for the local, for local p-Adic Langlands. So you construct a Banach L space it's going to call B of rho x, which has a unitary action, admissible unitary action, which satisfies the following properties. So such that so what's the first property? So if you look at the algebraic vectors, then this is just that factor. So this is the tensor product over all v dividing p. That Breuil Schneider representation of rho x restricted to gamma k v tilde, except there's this thing about the normalization. And this is dense. So in some sense, it's the completion of the algebraic vectors with respect to a suitable norm. And it satisfies local global compatibility. So if you take B of rho x and you tensor by that Eigen module, then this is isomorphic to the closure of those algebraic vectors, which need not be the whole thing. And then, of course, the flaring question is whether this depends only on the restrictions to P. And that I don't know. But you can relate it, at least in the crystalline case. So if rho x is crystalline, about P, there's this equivariant map from, I'm just going to write it down, so B psi x theta x into B of rho x with dense image. Well, I don't really have time to define this in detail, but this is the coarse p-Adic Langlands of Schneider and Teitelbaum, which only depends on restrictions to P. Okay? So in particular, it implies that this guy is non-zero, which was conjectured by Schneider and Teitelbaum. Okay?